So in this section, 4.5, we're going to learn about limits at infinity. Now you might notice that we were in section 2.5, so it makes sense to call the next section 2.6, but the book doesn't do things in quite the order that I prefer. If this makes you nervous, please go back and re-watch the Karate Kid video again. Trust me, that Limit Man here is not going to lead us astray. So remember way back when we started thinking about limits, we said there were two things we wanted to do. First of all, we wanted to think what happens when things get small, and that's what happens with the limit as x approaches 0. This is saying what happens to this function when x gets really small, gets close to 0. And if we look at this, this really looks like 0 over 0. If you just go ahead and put 0 in there, it looks like the numerator is getting smaller, the denominator is getting smaller, so who knows what's going on. But what we learned how to do is we learned some techniques for dealing with this. And for this one, we learned that we can factor. And once we factor, we can cancel. And what we're left with is a limit that we can compute. We can actually just go ahead and then sub in here to get 2. That should, of course, be an x. And so we see that this limit isn't 0, it's not infinity, it's 2. Well, now what we want to do is we want to start thinking not just limits as things get small, but limits can also help us figure out what happens as things get large. And the thing we're going to be concerned with is the number of rectangles. So remember we said that one thing we wanted to do was we wanted to calculate areas of this blue region. And what we could do is we started by saying, well, let's make 2 rectangles, and that gives us a good approximation. But if we make more rectangles, we get a better approximation. The issue is that we need a lot of rectangles. So in this section, we're going to figure out what happens as we build up lots and lots of things. That is, what happens as x gets bigger and bigger. So let's look at these symbols here. We have the same limit. You know, this part hasn't changed. We still have x getting towards something, and we've got a function here. But now we've got the new idea here, which is this fancy sideways looking 8, which is infinity. And so what this is telling us to do is this says what happens to the function as we put in larger numbers. And so this is the question these symbols are asking. What's happening as this gets bigger and bigger? And if we wanted, we could just try to plug infinity in. We could say, well, infinity squared plus 2 times infinity all over infinity squared seems big. But this is another one of our indeterminate forms. We can't exactly say what's going on yet because it's infinity over infinity. This could be 1, this could be 50, this could be almost anything. And so one thing we can do to try to figure this out, or try to guess what happens, is we could make a table, or we could look at the graph. Now, the graph is tough to look at down here because, well, it looks like as we're going down, if we follow along the curve, we're getting close to something, we're sort of leveling off, but it's hard to say what happens way over here on our graph. The only person who can really go way over there is Limit Man, and we're going to see exactly how to figure this out in a second. Another thing we can do, of course, is we can always look at the table to estimate what's going to happen, and so we can put 10 into our function. If we put 10 in, we get out 1.2. If we put in 100, we get 1.02. If we put in 1,000, we get 1.002. If we put in 1,000,000, we get 1.000002. I think you can see where this is going. We're going to get a bunch of zeros if we put in 1,000,000,000 and 2. So it seems like we're getting closer and closer to 1. However, this is quite a bit of work to do in general to solve these. We don't want to have to make a table every time. And so we want to figure out some better ways to figure these out. So now we have our formal definitions of limits at infinity. So let's let L be a real number. Then the symbols, the limit x approaches infinity of f of x is equal to L, means that as x approaches infinity, that is as x gets larger and larger positive number, then the function value approaches L. So graphically we get close to L. We say that as x approaches infinity, the limit of f of x approaches L. Similarly, we can go far to the left on our graph using large negative numbers to say that as x approaches negative infinity, becomes a larger negative number, then f of x approaches L as well. So if we look at the example below of the graph g of x, it's kind of hard to tell actually what's happening to this function as we go really far to the right, that is positive infinity, or really far to the left, negative infinity. Often we're looking at too zoomed in a picture to see what really happens. The graph appears to be leveling off, but it's hard to say where it's leveling off as we go to each side, so we need to zoom out. Once we zoom out of our graph, it's a lot easier to see what's happening in our graph. We can see that the limit, as x approaches infinity in this case, seems to be getting closer and closer to 2. We seem to be getting closer and closer to this horizontal line. Similarly, as we move to the left on our graph, we seem to be getting closer to a line as well. So this means that the limit, as x approaches infinity, that is negative infinity of course, of g of x, appears to be getting closer and closer to 4. However, before we go talk about them, and how to figure them out nicely, algebraically, what we want to do is we want to think a little bit more about this graph because it's kind of a neat picture. What we have again in this case is that as we get closer and closer to infinity, we seem to be getting closer and closer to the horizontal line y equals 1. And just like before, when we get closer to a line, this is called an asymptote, and in this case, it's going to be called a horizontal asymptote. So we'll say that the line y equals L is a horizontal asymptote of the graph of f if either of two things occur. Either it's the limit as we approach positive infinity, or it's the limit as we approach negative infinity. So what we can say here is that since the limit as x approaches infinity, as x gets really big, of x squared plus 2x over x squared equals 1, the line y equals 1 is going to be a horizontal asymptote. So here's a good time for a pop quiz. What is the maximum number of horizontal asymptotes that a function can have? 1, 2, 3, or as many as we want? And hopefully the answer you picked is 2. If we look at a graph, we're only going to get horizontal asymptotes in two places. One comes from the limit as we approach negative infinity, that is, as we move to the left on the graph. The other place to get a horizontal asymptote is as we move to the right on the graph. So that makes there are only two places that we can get horizontal asymptotes. These are very different from vertical asymptotes. So if we drew a graph, we can make as many vertical asymptotes as we want. There's a nice vertical asymptote, there's a nice vertical asymptote, there's a nice vertical one, there's a nice vertical one. First person to tell me what function this is wins a prize. I don't know about you, but I'm getting tired of looking at graphs to figure out these infinite limits. So let's look at a theorem that's going to help us be able to figure out limits without having to always look at a picture. So the theorem says that if r is a positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the r equals 0. Furthermore, if x to the r is defined when x is negative, then the limit as we approach negative infinity will also be 0. And we've got two more nice limits here. The limit as x approaches negative infinity of e to the x is 0, and the limit as x approaches infinity of e to the negative x equals 0. Let's think about why this is true. So suppose you have yourself the limit as x approaches infinity of 75 over x cubed. Well, according to the theorem, this thing is just going to be 0. But why is that true? It's true because you're going to take 75 and you're going to divide by big numbers. You're going to divide by 10 cubed. You're going to take 75 and divide by 100 cubed. You're going to take 75 and divide by whatever number that is cubed. And every time you do this, every time you put in larger numbers in the denominator, overall you're getting smaller and smaller, which means you're going to get closer and closer to 0 every time. So this is a really nice theorem that's going to help us out quite a bit. So let's look at some examples of how we can use it. So the best tip I can give you is whenever you're faced with something that you think might have an infinite limit, or at least we're approaching infinity, what you want to do is multiply both the numerator and denominator by the reciprocal of the largest power. So let's think what that means. Suppose we wanted to compute this limit here in number 1. Well, what we want to do is we want to look and find the largest power. So here what we've got is we've got an x squared. We've also got an x squared here. So 2 is the largest power. So what we want to do is we want to multiply the numerator by 1 over x squared, that's the reciprocal, and the denominator by 1 over x squared. So let's distribute this and see what we end up with. We're still going to have the limit part because we haven't taken a limit yet. We need to multiply the 1 over x squared by both terms. So we've got the x squared times 1 over x squared plus 5 times 1 over x squared all over 3x squared times 1 over x squared minus 3 times 1 over x squared. And of course we can simplify this, and feel free to simplify it a little more quickly in your work if you want to. So x squared times 1 over x squared, well, these terms just cancel, so all we're left with in this case is a 1 plus 5 over x squared all over 3, as again the x squared and 1 over x squareds cancel, minus 3 over x squared. And you can be saying to yourself, I don't really see how this helped. Well, here it's going to pay off. What happens now as we approach infinity? Well, the 1 doesn't care, it doesn't have any x's in it. Also the 3 doesn't care, it also doesn't have any x's in it. But this 5x squared is going to go to 0 because we're going to take the number 5 and divide by larger and larger numbers. Also, the 3 over x squared is also going to go to 0 because we're going to take the 3 and divide by larger and larger numbers, making it smaller overall. So we're left with 1 plus 0 over 3 minus 0 equals 1/3. Now it's important to notice, where did these numbers come from? This 3 was sitting right there, and this 1 was sitting secretly in front of the x squared. We've sort of got a 1/3 here. This is going to be very important in a second. So let's look at another example. Again, we look here and we see, well, we've got an x squared and an x cubed, so we want to multiply both the numerator and the denominator by 1 over x cubed. So when we multiply this through this time, well, we've got an x squared times 1 over x cubed plus 5 over x cubed all over 3x cubed over x cubed minus 3 over x cubed. It doesn't look any better right now, I agree, but this simplifies quite a bit. So the x squared over x cubed becomes 1 over x plus 5 over x cubed all over 3 plus a negative 3 over x cubed. And then we look at the terms. The 1 over x goes to 0, 5 over x cubed goes to 0, 3 over x cubed goes to 0, so what we're left with in our limit is 0 over 3, which is just 0. Well, where did these numbers come from? Well, what we can think, we had a 3x cubed here, and in our numerator there's really a secret 0x cubed we can add onto the front. So that's really where the 0 over 3 comes from. And as a last example, let's look at this limit. Let's take the limit as x approaches infinity of x squared plus 5 all over 3x minus 3. So in this case, we're going to do a bit of a cheat. What we're going to do instead is we're only going to multiply instead by 1 over x over 1 over x. This becomes the limit as x approaches infinity of x squared over x plus 5 over x all over 3x over x minus 3 over x, which simplifies down pretty nicely into x plus 5 over x over 3 minus 3 over x. Now in this case, the last two terms as we approach infinity are both going to go off to 0. So what we're going to be left with instead is just x over 3, which we know goes off to infinity because the numerator is getting really large in this case. So in this case, what we had is that the term in the numerator was much larger than the denominator, and therefore we ended up with an infinite limit. And what we can do is we can put all three things we've just figured out together into one nice theorem. So our theorem here says exactly what we've worked through previous functions. 1. if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. So this is what we figured out in problem 1, is that the exponents, the powers are the same, therefore we just need to take the leading numbers, 1 over 3, and our limit's going to be 1/3. Part 2 says if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. In this case, the degree of the numerator is 2, the degree of the denominator is 3, and therefore our limit's going to be 0, just like we found before. And finally, part 3 says if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. So that's awful, terrible grammar. It just does not exist. And in fact, it'll go off to probably positive infinity or negative infinity. And so we saw this in our third example. The degree of the numerator is 2. It's greater than the degree of the denominator. And we ended up getting infinity in this case. Might also get negative infinity, just have to watch out for it. So let's try one more. And so if we look here at this limit, we want to take the limit as x approaches infinity, that is a negative 2x cubed minus 3x, over 5x squared plus 4x plus 9. And what we can see is that here what we are is we're in case 3. The degree of the numerator is 3. It's greater than the degree of the denominator, which is just 2. So our limit does not exist. But what we can do is we can be a bit more precise here. The key to this theorem is looking at and realizing that if you're only dealing with polynomials, this other stuff kind of doesn't matter. All that matters is your first terms. So this limit is going to be the same as if we only looked at the first terms in our limit, which is negative 2x cubed over 5x squared. And then what we can do here is we can do some canceling. So this will be the limit as x approaches infinity of negative 2/5 x. Well, as x gets bigger, overall it's going to be negative, so we just have a negative infinity as our limit. The key with most of these is that you can kind of look at them sort of fuzzily. You kind of just ignore the other parts. You only have to look at the biggest powers. I know I said one example, but I could never count very well, so here's one more example. So we want to compute the limit as x approaches infinity of the quantity 7 minus 2 over x cubed. Well, there's two different ways to do this, but the easiest way is just to think about, well, what are the limits going to be separately? The limit is going to be as x approaches infinity of 7 minus the limit as x approaches infinity of 2 over x cubed. The first limit's easy, it's a constant, it's 7. The second limit is easy, it's 0, so our limit overall is just going to be 7. So the last idea to talk about is one we've actually been talking about for a little bit, that sometimes you can get infinite limits at infinity. So pretty often you'll have functions that also just, as you put in bigger and bigger numbers, get bigger and bigger. Or as you put in more negative numbers, they get more negative. So let f be a function defined on the interval a to infinity. The statement, the limit as x approaches infinity of f of x is equal to negative infinity, means that as x approaches infinity, as x gets bigger, then f of x approaches infinity. F of x gets bigger. It just continues to increase. Similarly, we have a definition for negative infinity. It just means it continues to decrease. So let's look at some of these in action. So if we look at this thing here, it definitely looks like the idea that it's in this infinity over infinity indeterminate form. So what we want to do to compute the limit, well, there's two different ways to do it. One way to do it is we could simply look at it and say, well, the degree here of the numerator is greater than the degree of the denominator. Another way to do it is with polynomial long division. So by polynomial long division, this is going to be the same as the limit as n approaches infinity of the quantity 5n minus 5 plus 5 over n plus 1. And we can think individually what's going to happen to each of these limits. Well, if we think through individually what happens, this first one is going off to infinity, the second one is just going to be 5, and last we have 0. And we know that we can write that infinity minus a constant plus a constant is just going to be infinity. One more example. Oh, nice, this one has trig in it. So let's take the limit as n approaches infinity of n squared minus n times the cosine of n over n. Now with this one, it's not as easy as just looking at the first numbers, n squared over n, because that rule only applies for rational functions. This is not a rational function. The cosine means we need to do something a little more, but it's not that bad. All we need to do is we need to break this up into pieces. So this is the same as writing n squared over n minus n times cosine of n over n. So remember, this is just unadding our fractions, breaking them up into two fractions, and then each one of these is pretty easy. The first one will be the limit as n approaches infinity of just n after simplifying, minus the limit as n approaches infinity of cosine of n. Now, what's really neat here is that this limit ends up being infinity, because the n's getting bigger, and this cosine term is just wobbling back and forth between -1 and 1, but overall our function is just getting bigger and bigger and bigger, going to infinity. I encourage you to graph this function. It looks kind of neat to see what happens. But now you should go and post a question you have on Blackboard, as well as try the problems that are posted on Blackboard. And as always, if you have any questions, please let me know, and please ask in class. Thanks.